Hello guys, welcome back to the channel. It's the Caribbean Bookworm, and in this video I wanted to take the physics outside of just being indoors, being with our little bookshelves or talking just about physics in this particular fashion. I wanted to share something with you guys, which typically I try my best not to do, as I want this channel to be strictly a physics or bookish channel, and that is talk with you a little bit about a personal adventure which I've been on quite recently. My local university organized a university trip to CERN and Geneva very recently in the month of February. So I basically was for almost a week at CERN on site, and it was incredible. But not only that, throughout the weeks, there were things which I thought that you guys might definitely enjoy seeing as content on this channel. That namely being a lot of bookish goodiness that is relating as particularly to physics. So for those of you who are at my channel for like just for general bookish related content with no interest in physics, perhaps this video may be a little bit more boring for you, but to those of you who generally like physics and like seeing stuff regarding physics, then do feel free to stick around. I swear and promise that this will definitely be worth your time and quite interesting. So the manner of which I will talk about this whole experience at CERN is that I definitely will want to highlight the library I went to, like the library at CERN, because that definitely was one of the highlights for me of the whole trip, like just the amount of books, mathematics, physics, and just general books that that library has, like all in just one little, you could say, room or building. But on top of that, I will also talk a little bit about my general experiences with having gone there, the site, some of the experiments which our group was able to see, and things like that, and perhaps a little bit about Geneva itself as well. So I will break this video down into segments. I will talk for the first part about the experiments which we were able to see, so the science that was going on at CERN, because I think that that's rather interesting as well. In the middle of the video, I will talk about the books which I saw, which were many books basically. And then at the last part, I will talk a little bit, perhaps a little briefly, about Geneva itself and how I experienced it. So on the first day after we arrived at CERN, so one day of rest and then the following like schedule ensues, it was a day at which we were allowed to visit the LHCb experiment at CERN. Now, LHC stands for the Large Hadron Collider, and that's one of the bigger colliders that CERN has now that accelerates protons to relativistic speeds, such that you have a bunch of, you could say, atoms of or nuclei of well, protons or hydrogen that smash together, and from that you get these jets going out, which can help you study basically the fundamental building blocks of matter. Now, that is what the Large Hadron Collider in general does. Now, at the LHCb experiments, physicists are typically interested in this particle called the B meson, and that is a combination of quarks which make up this particle, which when it decays, it decays into things called beauty quarks and or bottom quarks, and alongside many other, you could say, smaller constituents. And physicists are particularly curious about this because the decay of these B mesons can allude to differences between the amount of matter and antimatter in the universe. As the fundamental question which physicists are interested in tackling with this experiment is that why there is an abundance of matter in contrast to antimatter in our observable universe. As we look around us, the world is mainly made out of matter, which the difference would be that if you have antimatter, you'd have a lot of particles which we would see in our day-to-day lives, or not see, but see the influence of, such as electrons and even larger things like protons and neutrons. The antimatter constituent of these things would just have an opposite charge. So the antimatter of an electron would be a positron, and of a proton would be an antiproton, etc. But we don't see the abundance of these things in nature. If we did, we would be able to pick up signatures of these equal abundance of matter and antimatter, because as these two type of particles come into contact, they would, you could say, produce light through a process called annihilation. So the fact that, for example, astronomers don't typically see gamma rays being produced from possible annihilation events all the time at a very significant rate implies that the universe itself was made with an abundance, perhaps, of matter and antimatter at one point or another in its early phase. The amounts of matter basically dominated over the amounts of antimatter. So there must have been perhaps a mechanism which kind of made the universe go for a more matter dominated universe versus antimatter. So studying the matter antimatter asymmetry or CP violation is what mainly the LHCb experiment is interested in, and also the main reason we were allowed to go with this experiment is because likely some of our professors and like lecturers pretty much know like people would directly work on this experiment. This is one thing which my university is heavily invested in. So that was very nice to get this very close, you could say, contact with the experiment. We were also able to see one of the older, you could say, detectors, and it's impressive to see these large machines and how you have various layers of detectors which are meant for different purposes. Like some of them are classifying detectors, which basically are used to, where you could say, have a magnetic field which bend particles that are charged, and that allows you to know whether or not they're positively or negatively charged. But also you have other things like calorimeters and muon detectors and other things which kind of help you distinguish the different type of particles that are produced during these collision events. So all of this was quite interesting physics, and not just the backbone like of what is happening, but also just on the experimental side, like all of the detectors that go into this thing, all of the precision that needs to take place, and also all of the engineering and technician work that is behind this. That, I think, in general is the thing which I found the most impressive at CERN, like seeing how the accumulation of a lot of people working together allows people to tackle these very fundamental issues and problems. So we were able to see LHCb. It was quite interesting, as you could see in some of the videos which perhaps I showed, or pictures. On that first day, beyond the LHCb experiments, we were also able to see the supercooling facility at CERN. This is a place at which people create superconducting magnets which are necessary for the Large Hadron Collider. This is very fascinating thing because it shows not just the high energy part of CERN research, but also showed the condensed matter part of CERN research, which I find to be equally as important. When you cool down metals to low temperatures, you get this property in quite a couple of metals known as superconductivity, which was discovered much earlier, of course. And this phenomenon allows you to create very strong magnetic fields, so very strong currents, for very low voltage, because superconductivity implies that electricity can flow through a metal with minimum, if any, if none, basically resistance. So you cool metals down such that the ion rosters of the metals, basically, so the positively charged nuclei of a metal or an alloy, is moving so small that there are minimum jiggling in this atomic lattice. And as such, electrons can move freely through the formation of these things called Cooper pairs. And basically, you have the phenomenon of superconductivity. Now, this means that these things can flow with minimum resistance, as I said, and this is very practical, not just in general, but especially for detector or accelerator physics. Because one thing which physicists really want is to be able to control the beam, which is basically used in these large colliding experiments. The beam would be like some small amount of, like you could say, protons or heavy ion. You have something like less than an Avogadro number of atoms, like 10 to the 11 atoms, for example. So a small patch of atoms, which starts at a particular, you could say, emitter, which I will talk about, and then goes into a various set of accelerators. And these are older experiments which are designed to basically accelerate the beam up to before it gets into the Large Hadron Collider, which kind of finalizes the acceleration and gives it energies that are approaching that of very close to the speed of light. Now, you need to be able to accurately steer these particles as they're moving in this particle accelerator. Now, luckily, these are charged particles because you ionize the beam. So, whatever atom you have, be it hydrogen or some sort of heavy atom, you go through various process of ionizing this thing completely, such that the only thing that is left is pretty much the nuclei of these elements, and as such positively charged particles. So if you have a magnetic field, you can steer them through the Lorentz force, and as such you can direct them in a path which is desired, be it a circular path or a straightforward path. Now, this is not the only thing that have to be taken into consideration. I'm confident that there is a lot more that needs to be taken into consideration, as the one thing I've noticed throughout this whole thing is that experiments in accelerator physics and such, and sensor equipment building and such, is such a vast and complicated amount of work, which it would be an understatement, whatever it is that I have to say. But one thing which I could point out is that there's a phenomenon at which the beam basically of like charged particles, which are moving in an accelerator, they want to disperse, generally speaking. So they tend to want to disperse, and accelerator physicists need to take this into account by creating or generating a magnetic field such that it can squeeze the beam path such that it remains kind of focally concentrated and doesn't diverge throughout the whole thing. This is done through a quadruple magnet, which I will definitely talk a little bit more about soon. But basically, these magnets, to get them strong enough, you need a supercooling facility, and that's also part of something we visited, which is very nice, hearing about the physics of superconductivity and its relevance in this field. Now, jumping into the next day, the following CERN-related activity which we did was seeing the place at which this beam is being produced. Now, there is an experiment basically called the LINAC, and this is what was used basically to start, you could say, emitting beams for these particle detectors. Now, the originator of the beam is called LINAC, or a linear particle accelerator, and there were various versions of LINAC that were constructed at CERN, like starting with LINAC 1, which is, as you can see in this picture, a very small apparatus, but could still accelerate proton beams to very high energies. And these proton beams were typically originate from just something as simple as a hydrogen tank, which I think was quite impressionable for a lot of people visiting the thing, because you think that these beams of particles would come from something much fancier than a hydrogen tank, but there we go. So when you look at the picture of LINAC 1, you can see these four little things in the middle, which kind of seem like this focal point. Each of these pins, you could say, would be things which would have a particular electric charge, such that it would be able to generate a magnetic field. So you can imagine that some of these things would produce a north and a south pole, and the other way around for the other remaining two pins. So if you have that, that means that you can have these various amounts of norths and south poles, generating a region in the middle at which any charged particles basically would be repelled by, because of the magnetic fields which are present. So this magnetic field, which is formed to this quadruple shape, kind of helps to focus charged particles into a single path without the charged particles diverging. Now, this is the beauty of this whole concept, which I talked about earlier, and this is exactly what the LINAC, you could say the linear particle accelerator, makes use of. It makes use of this along with these various tube-like setups to accelerate, you could say, the beam particles. So it makes it go faster and faster and faster toward each of these weird little toroidal shaped things which you see. A lot of this thing relies on both the physics of solid state as well as things regarding electronics. So there's quite a little bit of engineering that goes into this, which is incredibly fascinating. But currently, CERN uses a version of LINAC called LINAC 4, which we weren't able to visit because they are currently under maintenance and such. But the principle is still the same. I just imagine that the apparatus is much more complicated. But after this, we were able to also also visit the experiment called ALICE, which basically stands for a Large Ion Collider Experiment. Very straightforward. And the experiment here, or the detector of ALICE, is mainly focused on seeing what comes out of heavy ion collisions. So typically, you hear a lot about just protons smashing against each other and seeing what comes out of it. This is mostly of use for a lot of, you could say, particle detections and discoveries. But what physicists are also interested in is what happens when you collide a heavy or larger nuclei together. Such is the case with, for example, lead, which has quite a lot of protons in it. When you smash these things together, and especially as you have a bunch of, you could say, lead, you could say, nuclei that come in opposite direction and smash against each other, you get, for a very brief moment of time, a type of matter that forms that is known as a quark gluon plasma. A quark gluon plasma is a very interesting type of matter because it basically is a type of matter at which the quarks, which are typically confined in hadron structures like protons and neutrons, they become loose. They are not no longer in this confined state, but they are in this, you could say, fluid type of thing known as the quark gluon plasma, a type of matter which is heavily suspected to have existed in the early universe, fragments of seconds after the Big Bang, as well as in the core of the most extreme types of stars, such as neutron stars. So understanding quark gluon plasma is quite of relevance for fundamental physics, both on understanding cosmology as well as stellar astrophysics. So Alice is one of the few places, if not the only place, if I'm not mistaken, which produces this exotic type of matter. And of course, that was quite interesting to see because studying quark gluon plasma and studying the dynamics of quarks with a strong force through quantum chromodynamics are things which I myself am very much interested in. So it was amazing to see how theory is being tested in with these very large experiments. And of course, it took quite a lot of pictures, which you can see right here, and you can see these big concrete things around the actual detector. Perhaps I will show you soon what the detector would have looked like if it was open. But the reason it was closed was because, again, I think they were doing some diagnostics with the detectors, preparing it for a run that may start, if I'm not mistaken, soon, somewhere in the middle of this year. The cement little blocks basically that you see around the or in front of the Alice detector are things which cover the tube, because the tubes of the thing can be radioactive, because last time it ran, like, you have these particle collisions happening that are very high energy. So whatever scatters off from these collision events interact with the nuclei of the elements that are in the detectors themselves or in the environment. So they excite these nuclei and make them radioactive. You get things like beta decay and gamma radiation or X-rays. So all of these things which could be dangerous to humans at a certain dosage. So they covered these things with these heavy cement blocks. All of this was quite interesting, and I think I forgot to mention that when we went to visit the LINAC accelerator, we could also see the remnants of what is known as the Lear accelerator. And the Lear accelerator was built and ran till 1996, if I'm not mistaken, with a purpose to create anti-hydrogen. So not just the antiparticle of an electron and not just the antiparticle of a proton, which is already, I would imagine, something that is quite complicated, but an entire anti-atom, you could say, in this case, anti-hydrogen. And around this Lear experiments, what you may not be able to see in the picture is that there were also these cement, you could say, blocks, and that is because the site, you could say, is still a little bit radioactive, so you need to protect whoever is walking on the ground floor from the possible radiation that may still be coming off from the thing. So it's very interesting to see how with a lot of these particle accelerator experiments, one definitely still needs to think about some of the radiation risks that may take place because you're dealing with such high energy phenomena. Now, on the third day of experiment viewing, we were able to go to the Atlas building, and Atlas is one of the very well-known, you could say, experiments at CERN, and Atlas stands for a toroidal LHC apparatus, if I'm not mistaken, and it is the largest, you could say, general purpose experiment built at CERN. It is the experiment which discovered the Higgs boson back in 2013. It is a general purpose experiment in the sense that it looks just at many collision events and tries to, you could say, find something interesting from it. So you have collisions happening, and for reference, these collisions happen every, you could say, one collision happens every something like 25 nanoseconds or something. So very, very small fragments of a second. So in 1 second, you definitely have a lot of collisions happening. So a lot of data being taken in this experiment. This experiment also, as I mentioned with the other experiments like LHCb, and same principle goes for Alice as well. They're made out of these various layers which look for different particles which are kind of created in these collisions. And with Atlas, they just try to sort through data to try to look for physics beyond the standard model, so anything that may look interesting. Now, of course, this means that the technique you use for analyzing the data heavily depends on who is doing the data analysis. CERN has a typical protocol for kind of discarding like data that may not seem to be useful. That is done by certain biasing criteria and certain like statistical techniques for filtering. But this allows physicists basically to only look at events which may be of interest, and all of these marvelous technological challenges with data and such is what led scientists eventually to create the World Wide Web or the internet. This is why the internet originated from CERN to begin with, because of these large challenges with, you could say, data processing. But in our visit to Atlas, we got to hear about the things which Atlas is typically looking for, and but we weren't able to actually go the underground and see the experiment in person itself, because again, they were running through the diagnostics, etc. But we did get a nice tour of the Atlas building from both one physicist, which unfortunately I do not remember her name, and also Dr. Clara Nellist, who is a well-known, you could say, physics content creator on Instagram. I'll put a picture of her here. Definitely recommend you check out her content. She gave us a wonderful guide about the general area in the Atlas building, as well as some of the purposes, you could say, of the detector and the control room at Atlas. So on top of all of these days, on another day, on the last day basically that we were there, we were allowed to in the morning to see the remnants of one of the first, you could say, accelerators that were there at CERN. And this would be the super synchrotron accelerator. The synchrotron principle is one of the first matters at which experimentalists were able to steer electrons and accelerate them. It is a device which allows you to kind of steer basically electrons in a given direction by having just two giant magnets, which causes the electrons to move in a circular motion, again, to do the Lorentz force. We were able to see one of the first versions of these things and just look at how it was used basically, especially as an alternative to the way at which physicists were typically studying high energy particles back in the days, and that was simply through having bubble chambers. If you've seen videos of these things on YouTube, I'd highly recommend them. They're really cool. Channels like the Thought Emporium has some great videos on using cloud chambers to see radiation tracks from things like uranium and other radioactive isotopes. But in general, these cloud chambers allow you to see tracks that come off of various ionizing type of radiations, because these particles, even though they're very small, as they rush through a medium, they kind of ionize the atoms that are within that medium, so kind of bumping into them and exciting or removing electrons, and as such you have this sublimation type of reaction in the air, which kind of gives you this track formation. In a similar manner at which if you have an airplane that flies in high altitudes, you see them sometimes kind of leaving these vapor traces in the air. It's a similar process that happens in bubble chambers. And in the past, physicists typically studied fundamental particles and new particles by simply sending a cloud chamber up in a balloon in high altitudes, because they knew that in high altitudes the atmosphere is less thick, so you'd have more radiation from space basically that comes through these cloud chamber detectors, and they just have something to photograph these various tracks and try to look for like interesting new tracks which may tell you something about like new particles. It sounds very rudimentary, like they're able to, like, how were they able to eyeball it? But people were trained back in the days to recognize various tracks and what each of them may mean. But because you cannot control basically what types of tracks you get from cosmic rays, physicists wanted to control basically the radiation tracks which they were able to study. So with that came the philosophy of building an accelerator here on the Earth, and that's where this synchrotron machine became really useful, and later the super synchrotron, as well as bigger and bigger accelerators. So this was not basically one of the detectors themselves, which we saw, but we saw what was used to accelerate the beam, you could say, in the collider experiments. So I guess in general, all that I've said concludes the scientific visit, you could say, that we had at CERN. There were, of course, many other things that took place, but I think the interesting, you could say, physics side of it, I think I've covered that pretty much thoroughly. The other thing which I greatly enjoyed about CERN, and what I said would be the second part of this video, was the library. Now, CERN itself has its own internally built library. This was quite recently, you could say, renovated, from what I heard from some people that I know that went there. And it is a library that is located in the big main building, basically, of CERN, and that is very much close to the theory department as well. So when you get into a library, it is a very nice, cozy library, as you can see as I just walk and enter the library, and it has a variety of book collections from astrophysics. You can see many well-known books. Like, I think I saw so many well-known books that it was unbelievable, like from Carl Sagan's like Comet book, which I didn't even expect to see there. Like, there were so many astrophysics books, to many other astrophysics books. I will simply like let the video play and leave you to watch, basically, because there were so many which I think if I talked about each of them, this video would be much longer than you guys deserve to like have it. So here you can just continue seeing me going through some books which I really liked seeing there. Now, just a little bit beyond the general physics and some of the astrophysics like book sections in this library, you could see also that there was a relativity section in the library. These entail books on both special relativity and general relativity, and there were at least two shelves worth of GR or special relativity books. The collection also had books on gravitational waves. It had some of the classic books, you could say, on gravity. So all in all, you can see that this was an amazing collection of books, which I have never seen such a vast amount of well-known physics books under one roof. It was incredible to see that. And you might even see me finding Covariant Physics, which was the book that I used for my Journey to Relativity playlist a while back. I even found that at the library, so which I did not expect. So that was a great find. So you can see that I pretty much really enjoyed this library in a nutshell. After the general relativity books, you get to the quantum mechanics book. So the non-relativistic quantum mechanics book. So these entailed books regarding general quantum mechanics, introductory quantum mechanics, to you could say quantum information, quantum computing, etc., etc. So you can see me going through a lot of these one by one or bit by bit. I think I will just leave you to enjoy the site, basically, and see whether or not you recognize some of these books. Now, after the quantum mechanics book, I came across basically the quantum field theory books, and those were again a lot of books. So, ranging from typical quantum field theory textbooks, which a lot of people know about, to books that are more specialized, such as the Black Book of Quantum Chromodynamics, which very soon you might see me go through. I saw books, for example, like Sidney Coleman's like lectures in quantum field theory, which I heard are classics, as well as many other QFT textbooks. Now, beyond the QFT textbooks, there was a small section on quantum gravity theories and, like, you could say, extensions and build ups to quantum field theory. So, the quantum gravity sections are, of course, a lot of books on string theory, including many very accessible books like Zweiback's, like, first course in string theory, which I heard from many places. It's a great way to go if one simply has undergraduate knowledge of special relativity and quantum mechanics. So it's a nice entry level way for undergrads to kind of feel the water a little bit as to what string theory is about. But of course, there were more heavy books like all of the Joseph Polkinski books on string theory, as well as many other books on the topic. But they also had books that were not string theory. There were books on loop quantum gravity. There were not many, but some books on renormalization group flow, which is another interesting technique that can relate to studying quantum gravity. There were books on causal dynamical triangulation and many other, you could say, approaches towards quantum gravity. So I'd say this collection also was well worth the check. And afterwards, you get to many other sections. So from classical slash Newtonian, you could say mechanics, to things like electrodynamics or electromagnetism, optics, you could say material science or condensed matter physics, and many more. I'll just let the video go on and you can see everything which I saw myself. And I perhaps will write some remark down of books which I thought was particularly interesting. Now, as you can see, I also found some particle physics slash nuclear physics books, which were also quite interesting. Now, near the study areas in the library and near some of the books as well, there's this really nice statue of Niels Bohr, which was given to CERN, from what I read, by Weizsäcker, which was a very well-known theoretical physicist at the time. And if you saw my video on the Shelter Island conference, you know that this person played a crucial role in the developments of quantum electrodynamics. So it was interesting to see the effects and fingerprints of so many well-known, you could say, physicists of the time that are just kind of there, you could say, for you to observe. If you walk in the library and go down some stairs, there is this like garden, which I didn't film because there wasn't much to see. But more interestingly, there were these posters that highlighted certain Nobel Prize winnings for people that were affiliated with CERN. From findings that related to soft matter physics, to findings that related to astrophysics, to condensed matter physics, and many more, including a really cool, you could say, comic that you can kind of follow as I continue with the video. Now, on top of everything else, which is already so great about this library, which makes you, especially if you're like me, and you really love these books, you really don't want to get out. There was also a bookshop, which there were like two glass doors connecting you directly from the library to the bookshop, and one door from the outside as well, like in the hallway, which also connected you to the bookshop. So many things lead to the bookshop, basically. And in the bookshop, you have as good of books which you could find in the library also there, basically, but the difference being that you could of course buy these books which you see there. So again, you can take a look for yourself. There were books ranging from astrophysics, like plasma physics and things like that, to books related to high energy physics, mathematical physics, and really just really good physics textbooks like accelerator physics, condensed matter physics, and many, many more. I've even gotten myself one book from this bookshop. I will talk about the book which I've bought in a small little segment, I would say near the end of this video, because I think the book which I've got, there's an interesting, sweet story to it. So I want to kind of close the video with that. But all in all, you can see that the CERN library and bookshop was for me one of the highlights. It is definitely a dangerous place, especially if you like books like this, like very technical books or popular science books as well. Like it has everything, and that is exactly what makes it dangerous. It is a library just filled with physics books, basically, or math books. Now, beyond the CERN library and book shop, which I wanted to talk about, the last bit which I wanted to briefly talk about was the city of Geneva itself, which, to my surprise, was not quite as close to CERN. CERN is a little bit on the outskirts, that is basically a little bit outside of Geneva in a small town called Meyrin, and it's very much close to the Geneva airport, but even closer to the border between Switzerland and France. So it is really much more on the outskirts than one would imagine that that's where CERN is located. But Geneva itself is a gorgeous city. One could take the tram basically from CERN all the way to the city center, and you can walk and explore the city. It looks very nice. If you've seen a lot of European cities, you kind of know loosely what to expect already. Like you'd see a lot of tram lines and a lot of like bus connections and such. So you might not be quite as surprised by the city of Geneva itself if you were to visit, for example, yourself. But one thing which is remarkable about the entire area which you're in, like at CERN or in Geneva, is that wherever you look in the far distance, you see mountains. Like even when we were arriving like to Switzerland, where we were passing the French border and entering Switzerland or driving near the Swiss border, you could see basically all of these mountains around you. And it's something that is astonishing to see, because you'd see these mountains with snow all the way at the top. So you know basically that it's it might be quite cold basically there, or at least cool enough that the snow does not immediately melt away. And the scenery which you see wherever you're walking in the city or whatever it is that you're walking, you just see mountains everywhere around you. That is an incredible sight. Like that is something which is amazing to see, especially if you're not used to seeing very tall mountains. Like it's a whole experience in and of itself, and it's a gorgeous scenery. But Geneva as a city itself, if you pass the areas which you drop off typically with a tram and you continue to walk a little bit more inwards, the city does start to get its charm. On the basic middle parts of the city, where, for example, if you walk a little bit towards the bridge, you can see the famous fountain spring. It looks a lot like a typical European city, as I mentioned, like a little bit of Paris and a little bit of other like European cities. But if you walk a little bit more inwards, then it starts to have also this like Swiss charm, as I kind of call it for myself. Like it feels like a European city, but it also feels a little bit more calming and kind of it looks expansive is kind of what I want to say, because Switzerland is also quite expansive. If you go, like, you will feel the difference between Swiss francs and euros or US dollars or whatever currency you have. You'll notice that Switzerland is a quite an expansive country, but it's worthwhile to visit because it does, to a lot of degree at least, feel safe, depending on how you move, of course, in the city, and take into account that it is a big city, and also it is quite clean. So you do see that, okay, there is a place at which all of this money is going into. So as you can see in maybe some of the clips that I showed you or pictures, Geneva itself is a very pretty city, but I have not seen other Swiss cities, so I cannot compare it to anything else. But I did like what I saw. So to tie everything together, like I had quite a lot of fun seeing a lot of the science that went on in CERN and just being on CERN in general, because that has always been one of my goals and dreams, basically, to just visit CERN. And I was so glad to have been able to do that through like my student like trip, like you could say, thing that was organized. But also I hope to in the future definitely go back. Like I like just the general feelings and atmosphere that I got at that place, the camaraderie between different people from different nationalities. Like it is such an international environment, which was incredible to experience. And also, of course, I like the library, I like the bookshop. Like it's the place to be for books when it comes to physics and math. There is no better library or bookshop that I've ever seen that has so many physics content all in one place. It's incredible, as you could have seen for yourself. And also the city of Geneva itself is quite nice. You gotta know where you visit basically and where you stop and what things you want to see, but the city does have its charm. But in regards to the bookshop, I did get myself one book which I wanted to show you guys, and that is the book by Shrednicki, and that being his quantum field theory textbooks. I heard a lot of good things about this from Mark Weitzman, like the YouTuber, and many other people that talk about quantum field theory, mainly because Shrednicki's book is quite interesting. It doesn't start with this very, you could say, the structure which a lot of quantum field theory textbooks have, and that is like starting with classical field theory, starting with quantizing classical field theory, and then jumping immediately into representations and groups in quantum field theory, and then slowly building up to like quantum field theory stuff, like things getting like LSZ reduction formula, propagators, Green's functions uses in like these QFT calculations, etc. It actually starts by developing all of the mathematical machinery which you need to do QFT calculations, but in a simple, like in a simpler framework. It starts with spin zero particles, so it concentrates on scalar field particles, and then it builds up to more complicated particles. So it goes to spin one particles, like other bosons, and goes on to things like spin half particles, which are fermions. So it develops the mathematical tools which one would need to do all of these QFT calculations, and it teaches you in a manner, because I've already started reading it, it teaches you in a manner which, if you've gone through a full, you could say, undergrad, I would imagine, in physics, and you've seen things like tensor calculus and you've seen special relativity especially, and you're just a bit, you could say, mature in your physics and math, you can easily pick this book up, it seems, and go through it. Like, I could definitely follow it because I know, like, my Lagrangian mechanics and Hamiltonian mechanics, as well as all of the other things which are needed to kind of be able to follow this book. But the book itself was not the only highlight. The highlight of the thing was that throughout my days at CERN, especially on one particular day, I met two very well-known theoretical physicists by pure coincidence, just because I think CERN is such a big international place where things are always happening. It kind of feels like the Hollywood for physicists. Like, you would see well-known physicists everywhere. Like, I saw so many people which I typically see on Instagram, like people that create content at CERN. Like, I just see them walking around or like eating at one of the restaurants, or I just see them like just having a talk with a colleague or a group of students. It was incredible to be in that environment. And in one of the days where I was just standing at one of the areas in the cafeteria in the big restaurant in the main building, I just saw the physicist John Alice. Like, he was just waiting in line there to get something to eat. And after he got something to eat, I kind of approached him, talked with him, kind of was a little bit nervous because I didn't expect to see such a well-known figure there. But the conversation was nice. He gave me some interesting tips and also signed basically my book for Shrednicki. Now, the reason I'm not showing that immediately is because I also met another well-known theoretical physicist later on that same day. On that same day in the cafeteria, I've met Fernando Quevedo, and Fernando Quevedo is a Guatemalan theoretical physicist who was basically the director for a good portion of time of the Abdus Salam International Center for Theoretical Physics. This is an international institute at Trieste in Italy that is basically concentrated on kind of encouraging physics in developing countries, something which is quite near and dear to my own heart. So it was very interesting to talk with him about this to begin with, and also the fact that we could relate quite a bit when he found out that I was from the Caribbean. So there was a lot of common ground to talk about. So I talked a lot with him about string theory, his work, and also the things he's been doing, like at CERN, and his experiences in general. And I managed to get his autograph as well, and just had quite a very meaningful interaction with him. I won't get into all of the details, but it's simply said I greatly enjoyed meeting Fernando Quevedo and talking with him about physics, his experiences, and everything in general. So for that, the two signatures which I now show in the video are things which were just these things were like meeting these two physicists was definitely the pinnacle and highlight of my entire trip. And that's why I wanted to close the video with this, because I wanted to state basically how nice it is basically to meet people that you kind of seem like they kind of seem like untouchables to you, right? Like, they feel pretty much like celebrities, although of course not everybody knows these people because they're very much well known within the community. Still, if you're, you know, a budding aspiring physicist like you, in my case, I go to online conferences and see people talk, and that's how I see some of these well known respected scientists in fields that I care about. It's amazing to see them in person, and it's amazing to see how kind they can be and how approachable they can be, and how much alike, you could say, or how much human these people can be. Like, if one person has a question, like for example John Alice, I asked him something in particular and he was like, okay, I'm gonna type this on Stack Exchange and see the answer. Some little minute details like that which I didn't expect basically to see, even though like they're people just like us. So it's amazing basically to see stuff like that, and it's kind of inspiring in a lot of ways. So for that, I greatly enjoyed this aspect of my like trip, and I wanted to make a whole content out of this for you guys because I thought just it was a wonderful experience. And typically I don't like showing basically my personal life here on YouTube just for privacy's sake, but I think a visit to CERN is something that a lot of people could relate to, and I definitely hope that a lot of people that are either into engineering, physics, or any type of STEM discipline, be it in IT or something else, but you're kind of curious about CERN as an organization, I do hope you get to experience it because it's a wonderful thing to see, like, or at least once in your lifetime. So I hope you guys enjoyed that content, and let me know in the comments down below what you think of CERN, what experiments you find the most interesting, or what piqued your eyes about the library, or whatever thoughts you may have to share. I'd be very much curious to hear it. I don't think I will create a content like this anytime soon because it was quite a big content, but I do hope that you enjoyed that which you have gotten right here. As of course, for me, the thing was just incredible and I really wanted to share it with you guys. So I hope to see you guys soon for more content and stay tuned for more videos. Bye bye.